hosting the session on industry opportunities. In this session, we deviate slightly from the usual focus on research to take a peek at what is in store for us after we graduate. So I'm certain that all of you will agree with me when I say that embarking on a PhD is a daunting task. What could be more daunting, however, is building our own careers post-graduation. So the main question on our minds is to pursue a postdoc or not. And if we do so, how do we plan our careers to reach our maximum potential? If we don't pursue a postdoc, what other opportunities await us? To help us answer these questions, we are very fortunate to have 4 guest panelists who will be sharing with us both their technical expertise and career development paths. They will each give us a short talk, and this will be followed by an informal panel discussion. So I'll just ask that everybody keep their questions for that discussion. Okay, to start off the session, it is my pleasure to introduce Mr. Lu, founder of Biosensors International, to share his working experience. Mr. Lu received his training in engineering at the University of California at Berkeley and Masters in Business Administration from the Thunderbird Graduate School of International Management in Arizona. Having amassed more than 30 years of experience in the medical industry, he is certainly an eminent figure in the industry. Please join me in welcoming Mr. Lu. Mr. Lu, please.
Thank you very much for the long introduction, and it's a pleasure to be invited to be in front of young, aspiring, I guess PhD candidates or PhD graduates, students, candidates. So, how many more years to go? Most of you? Depends. Well, although the topic that I was given or asked to share with you is technologies, and I like to be a little bit unorthodox just by sharing you without people, without talent, there's not going to be any technologies, and also sharing with you why I think you have a bright future, being in just the right place, the right time, which is called Asia, and within Asia, perhaps Singapore. All right? So may I just start my slide? Do I push something myself? I guess I'm used to people doing it for me. Okay, where are you? Okay, how do I do it? Push this button. Okay. So, first of all, this is something maybe very trivial, but I just wanted to serve this as a reminder. Asia, more than 60% of the world population resides in Asia, as you see in this chart. And out of which, India and China are by far the biggest. And a lot of times people may think, so what? But the truth is, this is a great asset, And if you have all this many people, just can you imagine how many genius you can produce? Like what I see some of you here. No smile, no laugh? Give me a break. Be more proud of yourself. Well, the real story is the fact that, this is going to offer a much higher chance for all the people involved in Asia, young age, just to begin to really strive for a much better future as far as I'm concerned. Then the next one is just to look at the GDP by region. Again, I broke it down into China, India, Japan. These are the 3 known countries. Also, if you combine Asia as a whole, including all the 3 countries, and you compare the rest with the rest of the world, you quickly find out, GDP is, very, very strong and powerful, especially in the recent years. And it's already surpassing all of the European as well as the United States. And that also goes to show the degree of energy that Asia possesses. Then the next chart is the graph that shows how GDP has been performing in the last 10 years. And you can see it's very, very obvious. Asia, including China, India, Japan. Japan is not really necessarily included in there, but Asia, India, and China are on those rising, are on above the graph, whereas US and EU are really dropping down. And then with the way it's going, it is predicted by year 2020, even a country like Korea is going to surpass Japan. And of course, by year 2027, guess what? China will most likely surpass the United States in terms of the amount of the GDP. And these are the things I may not live to see, but you do. Now, with those background, knowing that we've got the right combination, because you're in the right region, where the population is big and the GDP is growing. But that doesn't guarantee any success, my friend. I think there are several things that you have to consider in order to really achieve so-called success. It doesn't come by itself. And the three ingredients I have pointed out here is people and technology, and least, if not the last, is the money. Let's take a look at the graduating people again. By again region. India, China, Japan, US, is that right? And the European communities. When you get older, you cannot see too well anymore. These are the annual new graduates in the field of science and engineering. So for those people who are in the humanities, I'm sorry. How many of you are humanities? Not too many? Okay, you're the minority, by the way. And again, this is an indication of, to us in industry, the future trend. How I can figure out where are the talents. Because if you have not the proper education, even if you are the smartest kid on the block, you may not have the proper education and talents to be exploited. So this goes to show, again, in Asia, we are showing a very strong trend. We are on the right track. And when it comes to technologies, needless to say, just anything you touch on these days, let it be TV, let it be appliances, computer, iPhone, smartphone, even toys, jeans, you name it. Virtually every one of them are manufactured in this part of the world. And we have certainly become the, manufacturing of the world. I mean, if I include the whole Asia as a whole, not just talking about India, China, or just single them out. I'm just talking about in this region. Then, just manufacturing alone? Come on. It has to be low cost, right? Otherwise people won't come. And low cost alone? No. Quality. It has to be low cost and low quality. And do anybody care these days where it's made? So long as it gives you the good quality, it gives you the good price. That's how everything moves, isn't it? Without technologies, this will not happen. So, for the mere fact that people have identified this region to be the place to manufacture, it's primarily attractive because of the cost, of course. But if you don't produce good quality, they won't come. And biosensors is one of the good examples. So we just wanted to point out you have the technology, you have the ability to acquire the technologies, and people are willing to give you the technologies. That's why they are here. Okay? Let's not be mistaken. Then, when it comes to the last piece, which is money, look at this chart, which is the direct investment or foreign investment into different regions. Again, Asia as a whole is higher than Europe and US. When I was young, I was inspired by American dream. And I was told, if you go to America, that was more than 40 years ago, by the way. You know, if you go to America, you can just find there are gold on the street you can pick up. It's just guaranteed you will be rich and you will be successful. And that's 40 years ago. And today, it may not be the same anymore because I don't find any gold in America. I find it's tough because of the high tax and the social issues. Okay? So people are very smart because money chases opportunities. And this goes into to show you money is now flowing into Asia more than any other region for a good reason, for opportunities, for success, for future. And you are in luck because you don't have to worry about not having enough money in this region. And here are some of the examples of leading Asian companies. A lot of times people tend to overlook, but there are many. Let it be Koreans, let it be Japanese, let it be Indians, okay? Let it be iPhone, let it be technologies, everywhere, appliances. It's amazing, that there are so many exists. I'm in the medical technology, so I have every intention to at least promote biosensors or medical industries to the graduating students. I hope you don't mind. Okay, but in the list that I just showed you, there's no medical device, there's no medical technologies shown. Why not? Again, it's a talent. It's a talent. 2 years ago, Biosensors took a very conscious decision to close down our operations in the US, where we did all of our advanced R&D research. We transferred, relocated to Singapore. It was a big decision. I lost 60% of our able, talented people. But I think we needed to make a decision just to see whether we want to have a presence, stronger presence in Singapore or in Asia, and if so, in Singapore, or we just continue to pretend that, nice and happy, that America gives us easiest way to get the people. But we did it. We think it's our job. Biosensors, which is now known to be a very successful biomedical medical device company today, even in the world, for our coronary stenting technologies and the sales. I think it's time Asia has the ability to produce and equip a medical device company. We are in a business called coronary stent. Does anybody know what's coronary stent? You do? Okay. You get a discount from me in case you need one. And just, where's Take Care? Oh, he's not here. Write down his name. No. A coronary stent is a metal tube that's delivered via a device called catheter. It's treated, it's a therapeutic device to be treated for the patient who suffers from coronary blockage. And that's very critical because if your heart is blocked, maybe within a few minutes you have no more life. So to us, it's a serious thing, and it's also to us that we are not only trying to serve this as a good business, but also try to believe that we provide a better quality of life or help people save their lives. Look at this graph, and you will see stenting. It's a little tube. It's as big as $7 to $8 billion US dollar term globally. And 10 years ago, 50% of this market was dedicated to the US market. 10 years later, last year, only 1/3 is now served in the US, 2/3 are now outside of the United States. Biosensors is running at about 340 million US dollar revenues, and has more than $100 million, we are all talking about US terms, profit. But we have not addressed the US market. The point I'm making is, sometimes opportunities are outside of the United States. And a lot of times, these things are being taken for granted as if unless you are in the United States, you cannot be successful. And my point to you is, today, you don't have to be in the United States to be successful. On the contrary, if you address properly, outside of the United States may present much better future. So you have to remember, as a young, inspiring, up and coming, the future and the trend is moving towards Asia. A little bit of background about biosensors. I founded biosensors about 20 years ago. We started out as a contract manufacturing for large corporations, just like I said, attracted by the low cost, better quality. Today, I started out with 20 people. I also started out with my own money. In those days, nobody believed in Asia, so I had no choice but taking a risk myself. And today, like I said, the company is listed in NASDAQ, and we are very successful. And we have more than 1,200 employees all over the world, with the exception of the United States. In Singapore, we have more than 400 employees. And we have manufacturing, we have research and development, we have sales and marketing. This is certainly our headquarters. And our growth in the last 3 years has been very phenomenal. And why makes biosensors successful? Not 100% because of the technologies. Also, cannot deny technology has played a very big role. We internally developed a proprietary drug. It's most ideal for treating the restenosis. It's a regrowth of the vessel inside of your coronary vessels. We managed to use that drug and mix it with polymer to control release, or to release over the time inside of the vessel, to gradually release the drug during 9 to it will be completely dissolved from 9 to 12 months period. And then by the time when you finish dissolving it, there's nothing left other than the bare metal stent, which is the main platform of so-called stent. And it's only coated on the outside. So the bloodstream that runs through inside of the coronary vessels remain to be just exposed and contact in the stainless steel, which is believed to be very safe for many years in the body. And we are different because 10 years ago when we started this approach and we tried to prove to the world, of course we got our IP by now, everybody was using a durable polymer. That means the polymer doesn't dissolve. And even after the drug is released and dissolved, people who receive the stent end up having a block of polymer inside of the vessel that is very, very uncomfortable because it's a foreign body, and therefore anything, if not careful, or any time when the patient gets to be irritated, there will always be a sudden, they call thrombosis, a sudden blockage of the vessel that will kill you. But again, it all sounds very exciting. In our industry, technology alone will not be successful. You need to have so-called clinical evidence proved scientifically in human that this is really going to be superior or as good as any others. So 4 years ago, we conducted a human trial in Europe. This human trial is very unique because we call it an ordinary all-comer trial. That means it's a real-world trial. We do not exclude selected patients in order to control the outcome. We just said anybody who comes randomly, we will give either one of our DES or we gave one that offered supplied by Johnson & Johnson. And this was conducted, we named the study leaders. And we just recently had a 4-year follow-up. That means those people who participated in this study, it's already been 4 years. And in the beginning, there was hardly any difference between the two. This is a graph that shows major adverse cardiac event. Simply put, any serious cardiac so-called incidents such as cardiac death, such as acute myocardial heart attack, and those are all included in here. After 4 years, we begin to see a divergence of the results. The one that we compare against was Johnson & Johnson's stent. In those days, it was perceived to be the leader. The difference was the drug and the polymer. The one used by Johnson & Johnson was the permanent polymer, non-degradable. Whereas for us, it's our own drug called biolamins A9 and degradable. And in terms of cardiac death, in terms of adverse effect, we begin to notice we are superior, we are better. We used to think it's almost as good, but gradually now we are approaching to be better. And this is something that do not lie, correct? This is statistics, this is the results. And if you are a patient that is to receive something like a coronary stents, and pretty soon you find out, if you don't choose correctly, you may die. Oops, I think I skipped this. Anyway, what's not showing there is, in terms of a cardiac death, by now we show 80% of the time, if you had chosen Johnson & Johnson, you had a higher than 80% of the chance you would die before biosensors selection. That's very, very scary. Well, anyway, I don't want to take any longer time. So what I would like to finalize, just to give you the take-home message is, in order to succeed, in order to really look at your future, don't forget, your talent means a lot. Also, don't forget the technologies that you learn and you know how to apply is also very critical. And it also requires some money in order to, make everything happen. And all these things are equipped that are available in Asia. And therefore, in my opinion, the future is in Asia. Thank you very much.
Thank you, Mr. Liu. Our next speaker is Dr. Adrian Yeo. To all the Singapore Polytechnic Life Science alumni members among us, he might be a very familiar face to you. And he is also a figure who has played a significant role in inspiring our research interests. So Dr. Yeo received his PhD over here from NUS, and he now holds the position as Deputy Director at the School of Chemical and Life Sciences, NSP, where he heads the Life and Health Science Diploma programs. He also holds an adjunct assistant professorship at the UNN School of Medicine, and plays roles in national accreditation programs for diagnostic laboratories in Singapore. So let us put our hands together to welcome Dr. Yeo.
Thank you for the kind introduction. I'm Adrian Yeo from Singapore Poly. As Sandy has mentioned, I hold dual portfolios at Singapore Poly. I'm involved in the academic school as well as in the R&D center. And for this afternoon's short briefing, I'll just mention the activities of the Center for Biomedical and Life Sciences. As an introduction, Singapore Poly is just across the road from here. It's almost 60 years old. We have 1,500 staff, both academic and technical, and all the ancillary people like HR, estates, etc. There are 16,000 full-time students and about 3,000 additional students who take part-time courses at Singapore Poly. There are 50 diplomas, full-time diplomas, and the diplomas are clustered according to 4 different clusters: architecture and built environment, applied and health sciences, engineering and maritime, business, IT, and humanities. So you can see it's very broad-based, all the way from business, accountancy, psychology, to engineering, to architecture, and of course the biomedical and life sciences. Now, where the Center for Biomedical and Life Sciences is anchored is in the technology development portion of Singapore Poly. We are one of 8 technology and innovation centers, initially set up to take care of staff who are interested in R&D. The TIC, and in particular the Center for Biomedical and Life Sciences, or CBLS, has morphed into an entity that is involved in both R&D and also in providing resources to academia. We are also part of this broad SP healthcare team, and under this healthcare team setup, we look at all aspects of healthcare, from aging population to hospital medical technology, to also the business aspects of healthcare. And our collaborators come from all over the world, and we've set up DesignWorks Singapore in collaboration with the University of Toronto, and Live Well Collaborative, which is mainly involved in Silver Age technologies and expert systems. This is together with the University of Cincinnati. But more about the Center for Biomedical and Life Sciences. Our focus area is on product development, it's on biomedical acceleration, and it's on training. We hope to make 2 important aspects, or rather we hope to make 2 important impacts. We want to work very closely. We collaborate very closely with the industry to make an impact. In particular, we translate many IPs that come from NUS, NTU, and A-STAR into commercialized products. Likewise, our activities in collaboration with industry and within the center itself, we hope to translate the knowledge we gain back into teaching. So you can see now that the people we're looking for to work in the center are people who have an R&D background, who have some commercialization experience, and at the same time who are interested in also teaching career. And how it works for our full-time academic staff is they usually bid for competitive grants, and these grants can come from NRF, Biomedical Research Council, etc. And once they get this grant, then they are moved into the center for the R&D activities. When they are in the center, about a quarter to a third of the time will be spent on teaching, and the rest of the time will be spent on their grant-related projects. We also have full-time staff within the center, and these are people who mainly work with industry. And again, we also bid for competitive grants to fund many of our projects. Some of the funding, of course, come in-house from Singapore Poly and from the Ministry of Education. But about a third of the funding is competitive and comes from within outside Singapore Poly. Now, in terms of product development, we have three main focus areas: molecular diagnostics, devices, and chemicals. And here's a snapshot of some of our products that we have licensed over the past 2-3 years. One was a reagent kit, real-time based PCR kit for rapid detection of hand, foot, and mouth disease that we licensed to MP Biomedicals from the United States. We've recently licensed a handheld medical device for solids to Zentic, and also a biaxial bioreactor. This is a collaborative project with NGS bioengineering, and that has been licensed to QueenCell, which is an offshoot of QueenTech Scientific. In terms of chemicals, one of our projects is in collaboration with NUS Chemistry, and this collaboration works on the Singapore TAN, which is a rapid ID kit of toxins and other impurities in water. And we hope to develop this as a version of point-of-care testing, but for water testing. In terms of biomedical acceleration, the center itself has incubation space, and we work with a number of startups. These startups are usually funded by Spring Singapore, and these three examples here, BioFactory, HistoIndex, and CellSequel, actually started with companies that are funded by Spring, who license technologies from IBM, A-Star, and we got them to Singapore Poly to incubate. So we offer them space, there's no rental. However, in return for being at Singapore Poly, they have to work with our staff to put up grants. They also have to assist us in the academic side by helping us to host student projects, and also to act as mentors and faculty members for some of the diploma modules. We are also being primarily an academic institution, very much involved in training, and many of these training are industry related or for industry. And we have worked with CDC, USA, WHO to hold technical workshops and training workshops for the region and many parts of the world. So again, we very much make use of our R&D staff as well as our academic staff to run these workshops. Right, so in conclusion, I just want to mention that we are always on the lookout for talent. We want people who like to do R&D, but who are also interested in teaching. Right? We also, of course, over time, have moved people who no longer want to pursue R&D as their primary focus back to the academic school, just as we move people from the academic schools who are interested in teaching initially, but later on felt that they want to continue their R&D that they had as part of their postdoc PhD training. And these are the people who bid for grants, and we slowly move them back to their research center. Thank you very much.
Thank you, Dr. Yeo. Next up, we return to more familiar research positions with our very own NGS alumni member, Dr. Jonathan Yeo. Dr. Yeo was from the pioneering batch of NGS students, so he's certainly familiar with all that we are going through right now. He is also a principal investigator at the Institute of Medical Biology and adjunct assistant professor at NUS. He works in the field of stem cell biology and has received several research awards, including the Philip Yeo Prize and Singapore Young Scientist Award for Science and Technology. So please welcome Dr. Yeo.
It's very nice to be back at NGS. It's also very nice to follow Adrian's talk because I'm also an alumni of Singapore Polytechnic. Well, today's talk, I'm going to give you a perspective of what's for you after your graduate study, and to give you examples of what you can do or what you can achieve going through a postdoctoral fellowships if you choose to do one. So I'm not given a lot of time. I think I'm only given 10 minutes, so I'm going to show you the most important data. Right, so I just came back from 2 days of MC, so I will cough throughout my talk. Right, so it would have been better if the talk is shifted to Wednesday actually. Or even next week. Right, so I'm going to tell you my key interest, which is which is embryonic stem cells and pluripotency, or what are some of the promises of stem cell research. And one cannot run away from talking about embryonic stem cells if one wants to talk about the real stemness, the real stem cells. So embryonic stem cells, just to cut short the story, is isolated from the inner cell mass of a blastocyst stage embryo. So for mouse, it's about day 3.5. For human, it's about day 4.5 to day 5 or day 6. So interestingly, upon isolations of these cells, one can actually grow them on petri dish, and they can be cultured indefinitely for very long periods of time, which really make them very useful and interesting. But this is not a trivial feat, because somebody is actually awarded Nobel Prize for isolations of the mouse embryonic stem cells. So in the middle, it's Sir Martin Evans. So he first isolated mouse embryonic stem cells in the 1980s. So it was not until the late 1990s that Jimmy Thompson from Wisconsin isolated the first human embryonic stem cells. Well, why is embryonic stem cell so interesting? Well, at the top is the morphology of the embryonic stem cell. So it's grown in colony formations or colony morphology. So it can self-renew, as I have told you much earlier, that it can grow indefinitely in culture plate. But the other main properties of the embryonic stem cells is that it can differentiate into almost all the different cell types of your body. So imagine, embryonic stem cells can grow into liver cells or heart cells that can potentially replace, your and help you in organ failure. So this is what makes embryonic stem cells so exciting for research. Well, several years ago, Conrad Waddington came up with this model to, explain, epigenetic or cell-fate determinations. So the ball at the top represents a cell with, propensity to differentiate into any pathway, and we call that pluripotency. So this is what embryonic stem cells represent. So as the ball rolls down the epigenetic landscape, it becomes more and more restricted. And at the bottom of the valley, we say that these cell types is fixed. It becomes a certain cell types. It is determined. And crossing between the valley will be impossible because of the high energy barrier, between them. So we now know that this model of epigenetic landscape determination is way outdated. In fact, research has shown that cells of one lineage can be converted into cells of another lineage if you know how. And cells from one lineage, fully differentiated, can also go back up the epigenetic slope and landscape to become cells of more potency. And perhaps the most dramatic examples of how cells can be reversed in terms of its cell fate is that one can actually bring the cells which are fully differentiated all the way back up to a pluripotent state, just like embryonic stem cells. And we call that reprogramming. So how can reprogramming be achieved? So the more general methods of reprogramming, there's two. So on the left is somatic cell nuclear transfer. This was how Dolly was cloned. So one can actually remove the nucleus from a fully differentiated somatic cells and inject this nucleus into enucleated oocyte, and transplanting these into a surrogate parent or mother, and then extract embryonic stem cells from the inner cell mass. In another method, which was first pioneered by Shinya Yamanaka a few years back, one can easily introduce 4 factors into a somatic cells, allow it to grow in culture for periods of time, and get cells known as induced pluripotent stem cells that behave very similarly to embryonic stem cells. So what is all these buzz about induced pluripotent stem cells? In fact, there are also rumors that Shinya Yamanaka will be awarded Nobel Prize for these perhaps in the next few years. So there's a lot of interest in this technology right now. So one can potentially get the somatic cells, for example, skin cells from a patient, introduce 4 transcription factors known as OCT4, SOX2, TLF4, and MYC, and get induced pluripotent stem cells known as iPS that behave like embryonic stem cells. And these cells can then differentiate into the many useful cell types. And because these iPS cells is genetically the same as the patient, one can potentially reintroduce these cells that are differentiated back into the patient without any genetic or immunology rejection. So this is the key promise of iPS cells technology and in regenerative medicines. Well, I cannot emphasize more on the importance of induced pluripotent stem cell technology, because just a couple of years back, before Obama came into power, we know that the Bush administration have policies that are really restrictive on human embryonic stem cells research. And in fact, I think 1.5 years back, when I was still in Boston, there came a time where a local district court in Columbia ruled in favor of restricting further funding for human embryonic stem cell research. And a lot of us not funded are still alright. A lot of my colleagues who were funded by the NIH have to stop work on human embryonic stem cell because that would be illegal. So work on induced pluripotent stem cell therefore bypass a lot of these legal, moral, and ethical issues that surround and restrict human embryonic stem cell research. Well, after graduating from NGS, I started my postdoc in Boston. I asked myself a few questions. So I want to work in pluripotency, in the field of pluripotency and induced pluripotent stem cells. So I asked myself whether there's a safer source of clinically available tissues for iPS cells induction. I also asked myself whether we can generate iPS cells that are safe for therapeutic applications. So first off, most of the iPS cells that were generated when I started my postdoc were, originated from skin. So there's a lot of disadvantage to skin, being the cell types for iPS cells generation, because one need to perform surgery, which may cause complications. It is therefore very difficult to get donors to come forward, to offer their skin cells for research. And because skin cells, you need to grow them for long periods of time before you can get enough cells for reprogramming. And because also skin cells are exposed to UV. So you don't know whether, that there's some compromise to the genomic integrity. So we ask ourselves whether we can get it from much easier source, for example, the blood cells. So what I did here was, in the Dailies lab, we had this blood drive, so I asked my lab mate, please come forward to offer your blood cells for my research. So we tell them that, it's really for the advancement of science. And true enough, I get no donor coming forward. But we try to attack them on their soft spot, have a good heart, My postdoc training is only for 3 years. I need starting cell material for reprogramming. So true enough, I get no donors at all. But when I tell them, the promise of induced pluripotent stem cells in regenerative medicines, in the future, these cells can go back into you and really, form what they call regenerative medicines for therapeutic purpose. I get many donors who, are willing to throw up their sleeve and come forward to offer their blood cells. And you guess what? Most of them are smokers and drinkers. So we started out with blood cells. On the left are, blood cells that grow in vitro. They are usually in suspension and single cell. So what we did was to, grow them for periods of time in cytokines, and then hit them with the viruses that contain the 4 factors. And over time, their morphology change. They become cells on the right. We call that the iPS cells that are stained positive for alkaline phosphatase that are also grown in colony formation. So these are just some of the characterizations. We showed here that our iPS cells are stained positive for some of the markers like OCT4, NANOC, and TRA160. So molecularly, they behave like human embryonic stem cells. And when we inject them into the mouse, they differentiate into the various cell types. So it shows that they are pluripotent. They are just like human embryonic stem cells functionally. So we got a cover story for this one. We like the cover very much because it tells the whole story. You just need a very small amount of blood cells, maybe even a finger prick, to get enough cells for reprogramming. And that is so much better than having to cut off a piece of skin for the sake of reprogramming the cells. Then I move on to the next questions. So how can I generate iPS cells that are safer for therapeutic applications? So in the first instance, we were using viruses to reprogram. In fact, back then the art was to use viruses, lentivirus or retroviruses. So in order to achieve the second aim, we collaborated with Derek Rossi from Harvard Stem Cell Institute, and we asked ourselves whether we can reprogram using synthetic mRNA. So what we did was to create the mRNA in vitro in a test tube, in the epitope tubes, introduce some base analog or base changes so that the mRNA can evade the innate immune response from the cells. So we found that we are able to reprogram cells from several fibroblasts like CF, BJ, all these are just names of the fibroblasts. But the key thing is we are able to reprogram using mRNA rather than viruses, which make it so much safer and easier. As you know, viruses integrate into the genome, so that the genomic integrity will be compromised, but not the mRNA. So we did some characterization. So this is OCT4 promoter. OCT4 is a key gene for pluripotency. We found that the original cells, many of the fibroblasts, they are highly mutilated at OCT4 promoter, but upon reprogramming, these iPS cells behave just like the human embryonic stem cells. So the control here are the BJ01 and the H1. So these are the human embryonic stem cells. So our iPS cells have the same profile as human embryonic stem cells. So we did microarray analysis and we found that if you just focus on the yellowish circles and the green circle. So the yellowish circles are the RNA-induced iPS cells that behave very much like the human embryonic stem cells in terms of their molecular gene expression. So you also realize that the virally derived iPS cells, which are the reddish circles, they are far further away from the human embryonic stem cells. So they are molecularly more different from human embryonic stem cells. We also showed that they can differentiate in vitro. So we tried to differentiate them into neuron cells and also the endoderm cells, as some evidence from the TUJ1 staining and the alpha fetoprotein staining. So likewise, when we inject them into the mouse, they differentiate into the various cell types. So we are very happy that functionally they behave like human embryonic stem cells. So we got this cover story, which we think are symbolically very, very appropriate. So this is a mythical Greek messenger god. So he was holding on one hand the blueprint for cell fate determinations. So as you can see, stem cell to different cell types. And he was holding on the other hand a single-stranded mRNA. So this symbolized that a single-stranded mRNA can induce cell fate changes. So some of my friends found it a bit gayish, but I think he looks alright. You know. Anyway, I will just end my talk with acknowledgement to my lab members. So Ping Xia, she's my postdoc. The long tour happened to be an NGS student, I think first year. So Hui Tong and Delon both are Singapore Poly alumni, Hui Xia and Zhe Kai. So I also want to thank my collaborators. So George Daly, he's my former supervisor, Steve Goff, James Collins, my co-supervisor for my postdoc, and all the others, including Lee, who fed back from IMCD, and his postdoc, Jermaine Goh and Hong Chong. But this is George Daly's lab, a very huge lab. The members are also very productive on all fronts, in their family as well as on the lab bench. So we have a lot of extended family members. So so George is the guy. George is not the guy in the middle. The guy in the middle is me actually. So George is actually the guy on the floor interlogging his leg with one of the senior scientists. So my respect for him. Take a cut after I've seen the picture. But it just shows the kind of very casual, very open environment that we have in George Daly's lab, and I really appreciate that very much. So when I was in Boston, Prof. Lee Baowen, the former director from NGS, made an effort to visit us, and that was very nice. So he gave us some of the very valuable advice on what we should do when we come back to Singapore. And all this stuff. So this is my lab. We call ourselves the JLO lab. It makes us feel like celebrities somehow, So, but my lab is not so big actually. So half of them are actually interns. So we have about 5 members, and so that was taken in IMB just a couple of months back. So I'm still trying to seek out the world best students that I can find. So I hope that if you know of anyone interested in doing a graduate study, whether it's under the NUS system or the A-STAR system, you can try to apply to my lab. And I just want to end by quoting James Watson, the discoverer of the DNA system, the DNA structure. Sorry, just the last sentence. The sharper those around you, the sharper you will become. So I hope I'm always looking out for students that can disprove me and that can show that I'm wrong, so that it's really a learning process, even as a mentor. I thank you so much for your attention.
Thank you, Dr. Will. Last but not least, we move towards the field of computer science and engineering with Dr. Ko Xing, who is an independent investigator under the Electronics and Photonics Department at the Institute of High Performance Computing in ASA. Oh, that was a mouthful. He received his training at NTU, and he has published extensively in more than 35 journals and conference papers. His research interests include quantum plasma and computational micro and nano electronics, plasmonics and photonics. I have no idea what I just said. So this will be an interesting opportunity for me to learn. So let us welcome Dr. Ko.
Thank you, Sandy. Yeah, hi, just call me Wishim. Yeah, I'm fine with people calling me Wishim by the name. And I've been working for IHPC for about 5 years. So for my talk, it's purely, I think, an outreach talk where I'll just share with you some of my personal experiences, and of course, from the students and co-workers who have worked with me, what do I observe, and the possible problems or expectations you have to manage after you have graduated from NUS and if you join A-STAR, or in particular the Science and Engineering Council. So for me, yes, I have a PhD, and you will get yours soon. So I have a Bachelor of Engineering for EEE, my PhD also from NTU EEE, and after that I've been working, actually halfway through my PhD, I actually convert into a project officer because NG was going through some structuring where they changed from a 3 years PhD program to a 4 years one. So that's when you transit from somewhere from a UK system to something nearly a US system. So we are one of the guinea pigs. Yeah. And then after I joined IHPC, the Institute of High Performance Computing, because I'm working mostly on computational sciences or computational physics, device physics in particular. And I'm now a scientist and IHPC independent investigator. This is a pretty new scheme within IHPC where there are a few of us who are given actual funding from the institute to pursue our own research. And of course, before that, I've been a team leader of, they call it a capability group manager right now with 16 PhDs in my team. Now, of course, the condition for being an IHPC independent investigator is you cannot hold any position. Yeah. Okay. So, of course, when we talk about IHPC or myself, we'll talk about my research. During PhD, I work more on charge transport and, of course, quantum tunneling. Might seems like an old topic nowadays because everything now is about quantum tunneling. But during that time, we did come out with quite a few things that matters. So after PhD, or after I joined IHPC, the focus of the group of my department in IHPC is totally different from what I did when I was doing my PhD. We are working on plasmonics, which is purely electromagnetic phenomena, where you have electromagnetic oscillations excited at a metal dielectric interface, and that can cause huge enhancement to electric field. And you put a dye molecule close to it, you get increased fluorescence, and therefore you get more sensitivity, let's say in the biosensor, etc. So, and my personal interest, something which I pushed very hard when I was at IHPC, is in terms of solar or PV, where we are focusing a lot more on thin film photovoltaics, device modeling, and work very extensively with experimentalists. Of course, when we talk about thin film photovoltaics, you are trying to target active layer that's less than 1 micron. Okay, the aim of my talk is to share with you some of my personal experience. Of course, I want to highlight the differences in expectation that you encounter. For example, during our PhD, which is right now, in an academic setting, or after PhD, let's say you join a research institute under the Science and Engineering Research Council. And of course, to share some of our personal experiences or stories, if you prefer, and hope you enjoy the session. Okay, why do I say it's the real beginning? Actually, you have to be really contented with what you have now, because life during a PhD, no matter how tired you are, it is considered a breeze as compared to when you do a postdoc or when you pay your own group. So, first thing, you don't have to worry about research direction. Why? Because the advisor tell you what you can do, and if you're motivated, study a couple of topics. But when you join a research institute, the institute has certain direction or certain focus. For example, let's say you join IHPC, if you're under the electronics products department, we're focusing a lot more on electromagnetic theory and all the applications related to that. So you must have certain particular background, and you do not study anything else. You're not supposed to, or you can do it in your own free time. My department director always say, of course you can do this in your own free time. So, and you're also expected to have initiative to pick up skills that require to solve a problem. Your advisor might give you a simple problem, or it might be a more complex problem, but usually it's solvable. But in a research institute, sometimes you're focusing on problems that are pretty much advanced, or you really don't know what will happen next. we are focusing quite a bit on cutting edge technology that might not be worth anything a couple of years down the road because nobody can make them. That's possible. But you are expected to pick up skills pretty fast. And I really like this 30-70 rule. During your PhD, at least for mine, I fail about 30% of the time. What does it mean? That means your advisor gives you a problem, you can't solve it within the 3 months that you've given you. So you have failed at that time. But in the RI or research institute, slightly different because sometimes you're working on something that's really cutting edge. There's probably only 1 or 2 papers on that particular topic. And you have to create the rest for yourself. And how to approach the problem, nobody can tell you because sometimes even the person who gives you the direction might have no clue how to start to. So you have to think how to start out the whole research yourself. So that's why sometimes we tend to get a bit discouraged because you fail more often than when you're doing your PhD, and you might think that I'm not cut out for the job. But that's not true. But that's just a real life example where you're working on something that nobody has done it before, or very few people has done it before. You just have to have the determination to just go on. And of course, you can always get away with poor presentation skills when doing your PhD because when our advisor tells you, can you please present this at our group meeting, you just say, oh, I'm feeling sick, I'm not feeling well, I have a sore throat. And you may really get away with this. Or when you're writing papers, you take 3 months to write a paper, and your advisors get fed up and say, I'll write it myself, it's okay. So, but when you're a postdoc, when you're a doctor in front of your name, you can't do that anymore. Because your advisor is not there for you anymore. He can't help you. You have to do your own presentation, and pretty much very frequent presentation, you're engaging on a very new topic, and lots of reports to write. So at the first glance, you might seem that they have more administrative work to do. You spend more time doing presentation and writing reports. But these are all part of the job because you need to keep some record. So that's why having a good logbook is actually good for you because if you are used to keeping a record, you'll find this is not a chore. It's very natural to you. And of course, when you're a student, networking is not priority. Because when you go for conferences, first thing is where are the good food and where's the tea break, right? Yeah. And you realize that your advisors don't do that because you usually go and look for their friends. And probably that's where the coffee is. Yeah, of course. So networking is very important after you graduate. And actually, when you are doing your PhD, this is the best time for you to network, especially between yourselves. So for the first 2, I think these are skills that you will pick up. Your advisors probably won't let you graduate if you don't have those skills. It means to pursue your own research. When somebody gives you a topic, you find your own way how to do a research, how to pick up the necessary skills to do that piece of research to solve that problem. But I'll focus more on the softer skills, where not everybody thinks that they can handle it. Because I have supervised students who cannot handle it and they get depressed. So you do not want to be one of them. Okay. First advice, you say, yes, if you know that you're going to fail more often than not, then you just take failure as stride. Because a failure is not a real failure in that sense. Because you do learn something from being unable to